Hello, everybody, and welcome to another wonderful day of PCAM. So today we're going to be looking at how we can use bomb calorimetry to provide us a lot of information about thermochemical properties. So as we developed last time, we can determine a lot of properties of the internal energy of a system as long as we know the isochoric heat capacity. Because as long as we know the isochoric heat capacity and the temperature change involved with the heat process, we can figure out the changes of internal energy, which in turn can tell us a lot about the heat or work of a reaction of interest. However, it turns out that trying to determine our isochoric heat capacities can be a little bit more tricky than you'd think. So oftentimes what we're going to need to do is make use of a bomb calorimeter to make measurements of heat capacities, as well as potentially changes of internal energy, which we can use to back calculate other properties. And in general, the major ideas behind a bomb calorimeter is I'm going to go ahead and put a sample inside of a system of known surroundings inside a isolated system. Usually you can think about putting our whole apparatus inside a system with insulating walls. That way we limit any amount of heat transfer, as well as isolating the system from any mass transfer, giving us again a true isolated system. And as long as we make these walls rigid, we also get our isochoric conditions. So we can again imagine our isochoric bomb calorimeter as being positioned in a container with adiabatic walls, where we're going to then have a sample chamber, which is going to be put in a fixed volume container. That way, any sort of reaction or change that happens within this container will in and of itself also occur isochorically. And then we'll be measuring the heat transfer from our sample to the surroundings, which is typically made of a water bath. And by measuring the temperature change of our water chamber, we can then determine any of the additional heat should have come from our sample chamber. So if I know how much the change in internal energy of my water, I can go ahead and determine the heat or change in internal energy of my sample by knowing that any heat lost from my sample is heat gained by my surroundings. However, one of the things we do have to watch out for is that it turns out it isn't going to be quite so simply as using the molar or mass or specific heat capacity of our water, because it turns out that we are going to lose a certain amount of heat to the diathermic walls of the sample chamber, but also no container is truly adiabatic, and so we may see some heat loss to the apparatus itself. So in practice, whenever you make use of a bomb calorimeter, we should always make sure to calibrate our calorimeter itself. Now, it turns out there's often many tricks we can do to calibrate our calorimeter. One of the classic tricks is a lot of our calorimeters come with firing leads. So you can imagine our firing lead is going to be some sort of ignition source in case I want to study a combustion reaction inside my sample chamber. And combustion reactions are typically one of the most commonly studied reactions inside a bomb calorimeter, because it allows us to determine such things as, the calories in an item of food. This is again just how much energy is going to be released from combustion, which is more or less an accelerated form of digestion. But it turns out we can also use these leads as a heat source of known quantity, which can then be used to determine how much the temperature of our surroundings changes when exposed to a known amount of energy. So we can actually determine the heat released from our firing leads, assume they are a simple electrical firing system, by using the current of our electrical leads, the time that we ignite the system for, so how long I fire the leads, and the potential bias between the leads. So, for example, you can imagine using a 120 volt current with a say or 120 volt bias with say a 10 amp current for 10 seconds. And this would be an example heat source. And then I can go ahead and measure how much uh, the temperature of my surroundings change and use that to determine our, our isochoric heat capacity of our calorimeter itself. It is worth noting, some people do want to try and use this to determine our specific heat capacity of the water, but don't forget there may be additional contributions besides just the amount of water itself. So in practice, we can use these firing leads to help calibrate or determine our isochoric, our calorimeter constant, or again, our isochoric heat capacity. And then if I know the isochoric heat capacity of my calorimeter, I can then try and isolate any sort of additional heat source inside my chamber. So we can build this around the idea of I may have, say, for example, a combustion reaction, which will produce a known amount of heat. And then I will also have a known amount of heat from my ignition source, which I should be able to calculate. By using my calibrated calorimeter constant and a measured temperature difference, this will allow me to know the amount of energy absorbed from the calorimeter and the amount of heat produced from the ignition source, which means that any remaining heat should come from the reaction itself. Now, if I know how much heat was released into my sample by the reaction, the change in internal energy of the reaction should simply be the negative value of this heat of reaction. And again, the reason behind this being the fact that this Q of reaction is indicating heat entering the sample, and that heat enters the sample because it's released from some sort of chemical reaction. And we'll talk a little bit more about energy changes from chemical reactions later. Now, I went through a lot of nitty-gritty details of looking at bomb calorimeters. Let's go ahead and illustrate this by working a specific problem. So let's go ahead and say that I have a calorimeter that I want to go ahead and use to analyze a combustion reaction. So the first thing I'm going to need to do is calibrate the system. So let's go ahead and try and determine the calorimeter constant for a calorimeter that has an ignition source that uses a 12 volt power supply that runs at a 30 amp current, and I fire it for 120 seconds. 120 seconds. Now, this will give me the amount of energy released by my firing leads, and with no additional reaction present here, this should be my only heat source, and thus should be reflected in the change in temperature of the water surrounding my calorimeter, which increases by about 5 degrees. So using this, let's go ahead and determine our calorimeter constant. And in this case, it should be fairly straightforward, as I need to start by analyzing the heat of ignition, which can simply be calculated from multiplying these three values together. But watch out, we need to take care of units. So it turns out that an amp is the same as coulombs of charge being delivered per second, and volts is the amount of energy, or joules, per coulomb of charge. So by doing these quick unit conversions, I can go ahead and figure out that my ignition source released about 43,000 joules, or 43 kilojoules worth of energy. So I can then translate this to the calorimeter constant simply by dividing the amount of heat produced by the change in temperature. So I end up with a calorimeter constant of 8.5 kilojoules per Kelvin. And again, one of the things you should note, heat capacities should always be a positive value, which indeed we have. Now, I went ahead and have now determined my heat capacity and the amount of heat produced by igniting my ignition source. So let's go ahead and use this to try and figure out how much energy is produced by the combustion of glucose, 1.8 grams of glucose, which I go ahead and throw in my sample chamber, ignite it for 120 seconds, and I see a temperature change of my calorimeter of 8.36 Kelvin. So how can I go ahead and use this temperature change to determine the molar internal energy of my sample? So first thing I'm going to want to do is figure out the heat of reaction, or the heat introduced to my sample chamber from the combustion reaction. So I can go ahead and just rearrange this first equation and find the amount of heat provided into my calorimeter, and then subtract out the amount of heat that was provided by my ignition source instead. And so we can go ahead and plug in these numbers, and we find out that the combustion of glucose provides about a little bit less than 28 kilojoules of energy. But what I'm really interested in is the internal energy of this reaction. So I need to go ahead and flip signs, because it turns out my combustion reaction is releasing energy, not absorbing it. So again, always pay attention to your sign. Similarly, we also have to look at the molar internal energy. So we have to correct for the number of moles of glucose combusted. So we can do this by simply taking our mass of glucose, turning it into the number of moles using our molecular weight. Go ahead and complete our equation, and it turns out that the heat capacity, the internal energy of combustion for glucose is somewhere a little bit less than 2,800 kilojoules of energy per mole. So this will this should help illustrate how we can use a bomb calorimeter to determine energies of reaction. So next time, we're going to try and move on from our notations of isochoric conditions and internal energy and start looking at isobaric. Until then, take care.